Len McGillivray, and I will chair this session. So we have an address by Professor Jurg Hulliger, the University of Bern. And Jurg is a prolific author. He does research that provides very important insight into materials chemistry that bears both a chemical and a very physical sort of approach. And I've always followed his papers over the years. I think we first met in a Riche in the late 90s. And we've certainly integrated a lot of the thinking that he does, particularly on symmetry and host guest materials for us, into our work. So without further ado, Jurg, the floor is yours.
Maybe this podium is more suited for Mike Jagger than for a scientist, but I will try it. At first, I would like to express my deep thanks to the organizer, and particularly to Gautam Desiracho for the very kind invitation to give me also this honor to present this lecture. What is the topic? We have heard a lot about crystal engineering, what it should be. This here is a demonstration of the following. We start from an entity and we have a purpose, as Daria was saying. And what is in between this entity and the purpose? Well, nothing but mathematics, physics. There is no space left for serendipity. In order to bring us to the point to understand things that in principle are elementary, but I will come back on that. So I would like to introduce them briefly and already attach some content to it that comes later. When talking about polar materials, we have to address these 10 point groups for crystals and these 2 groups for textures. Common to these materials with this symmetry is that there is an ax. This ax has an end which is, say, positive, and the other ax is negative. This is a very important feature because crystals may show a growth behavior along this axis, which is very different on the plus side as compared to the minus side. For materials appearing in my title, such as composites and natural tissues, these 2 point groups for continuous or textures materials are important as well. A common thing of all these polar materials is that they feature a pyroelectric effect. And that's the derivative of the polarization against temperature, creating a vector. Clearly, this vector can only exist in these point groups. Origin of macroscopic polarity for molecular-based materials. This is now very different from the community working with, say, ferroelectrics of inorganic compounds. Here, the aspect of the lattice is much less pronounced than in these other materials. So we have an asymmetrical charge distribution on the entities. These entities pack in a geometrical way, which is polar. Consequently, the object is then also polar. This is an approximation, of course, but it shows that the necessity of exchanging electrons between these entities is not a major issue. So we can consider them as gathered together, creating an effect. However, each of these molecules has a dipole moment. And this is contributing to an internal and external field, an electrical field. And this field has the strength of 10 to the power of 9 volt per meter, having strong implications on molecular properties we are going to calculate or to measure. So the first term of the multipole expansion, such as the dipole moment. How a polar state can emerge? Well, there is a classical part, that is the nucleation. That is a highly cooperative process followed by a consecutive mechanism of growth, which is more an attachment process by individual entities, so having not a strong cooperative nature. Now, I will talk about materials that may nucleate into a non-polar seed, and then a growth mechanism allowing 180 degrees orientational disorder at the growing surface can lead to polarity when the material is developing in one direction. This will be called stochastic polarity formation. It can also be that probably by kinetic control, a seed is already polar, and then the same mechanism is applied to the growth. And we will see that in this case, the crystal can undergo a very particular transition into a bipolar state, in the sense that in one direction of the polar axis, all the molecules turn around. So we get a bipolar object at the end. I mentioned particular properties of crystals. We know from textbooks, this is very well known, that in principle such materials show charged surfaces, as we see this on this chart. However, we have no concrete view on that concerning experimental knowledge, especially not for molecular crystals. This here is the first calculation of the charge distribution in such a material having MM2-point symmetry, consisting of a polar molecule, 4-iodo, 4-nitrobiphenyl, to which we will come back. With Piero Macchi, we were able to calculate these charge densities on these faces. It shows clearly that it is polar, because this is red and this is blue. This is the iodo side, showing a very diffuse charge distribution, whereas the nitro side shows a very localized charge distribution. Interesting to notice that also the prismatic side faces show charge, but of course the charge on this face and the front face will be the same, and here as well. So this is about the charge distribution we have. I was addressing the effect of the strong field on simple properties of molecules. This here is a calculation of the average dipole moment in the crystal on the action of this molecular field. So this here is the free molecule value according to quantum mechanics. And then we have three curves showing three types of shapes of crystals. A cube, rather constant, a plane going down, and a needle even surpassing the free value of the molecule. Maybe some of you remember the work of Spackman. He has spent a lot of work in doing that, but he did it in a completely different way. He was assuming Ewald solution and Lorentz tensor formalism. So for him, the crystal is infinite large and more or less a sphere. Now this is much more closer to reality, because a needle, a cube, and a plate will behave completely different. What is this? Yeah. These charges of this crystal may be present in the high vacuum, but in a real world, as a laboratory, there are external charges that can go to this surface and make a charge compensation, as indicated here and here. Experimentally, we know practically nothing about that. What are the charges and where they go to? I will come back to this. Now the question is, what is the influence of this charge compensation on the molecular properties we just calculated for a crystal that has charged phases in the high vacuum. Again, on top, you see the case of non-compensated charge. Below, there are the curves for the compensation. You see that in principle the curves are bent like above, but now the plate is going up and the needle is going down. So in principle, this needle will go to 0 for an infinite length. If you ask yourself how much charge we have to deposit on a unit phase of the unit cell in order to make the charge density 0 at the surface, you have to deposit, depending on the site, 0.05 to 0.2 electrons. So this is a fractional amount of a full charge. The question arises how the crystal does that. Because one charge will compensate quite a large area. Therefore, is this a static effect or is it a dynamic effect? Is the charge moving around? This is all unknown. Because of this, we would like to investigate crystals that have no access to charge compensation. Because of this, we have constructed this machine where the crystal will be placed here. I show you another picture thereafter. And by this double guillotine, we can cut its end in the high vacuum. And then, by this capacitor, we can apply a field and measure the torque. Knowing the spring constant of this holder here, which I'll show you in the next slide, we can calculate the effective dipole moment of this object. I cannot present now the first result of this nice machine, but I can present you this here. This is a resorcinol crystal that we have grown in solution or in the vacuum. That's not so important. But this crystal has seen the normal environment. And then it was placed into the high vacuum. Some molecules have left the crystal, and then we switched on the electrical field. And you have seen, while the film was running, that for plus it was going down, and for minus it was going up. So only a polar object can do that. And only a polar object can do that. Now, is this dipole moment that we have measured here in agreement with an estimation of the charge on the dipole moment? We have found that in this simple experiment, the charge compensation is still about 99%. That means by evaporation we cannot remove these charges. Also, it is known that cation molecular complexes have a negative delta G. This is not true for anion molecular complexes. Nevertheless, it is such that we obviously cannot remove them. Maybe we can remove it by cutting the crystal. I'm moving to the next subject, which is very fundamental in crystal growth and needs resolution. That is the strong anisotropic growth of some polar crystal along their polar axis. We know the case of resorcinol, which was elaborated in the last year by John Sherwood at Strathclyde with many, many details. Then we have a nonlinear optical crystal, such as coamp, where we were working on it, and metanitroaniline. If we compare these three systems, we find that the resorcinol is growing from the negative side, the coamp from the positive side, and metanitroline has no preference. I will go back and start the film again. Here is the polar axis. Now some elongation takes place. Now we start to evaporate, and then we regrow the crystal. And you will be able to see that there is no preference, no obvious preference for the speed, which is larger in one direction of the growth. So we have a perfect contradiction between alpha resorcinol growing from the OH side, coamp growing from the amino side, and nitroaniline having no preference. That asks for a general theory. Dirk Zahn in Erlangen has done a very nice simulation for the resorcinol in the melt. This here is the seed. And then he was waiting for 5 nanoseconds, probably for conditioning the system. And then he waited 25 nanoseconds, so 15 nanoseconds later. Now what happened? On that side, which is the H side, where grow is not known to be effective, he found a layer which is incomplete. So this is not real growth. But on the bottom, where the growth is effective, that is the OH side, he found 2 layers. So we can say the intrinsic behavior of that system, far of any solvent, because in literature it was often claimed that the solvent played the essential role, we can say growth on the OH side is more effective. This is about what we know by today for this important topic. I come now to main principles behind stochastic polarity formation. In the 19th century, it was very popular to find a mechanical analog to explain theoretical aspects. I will do here the same thing, and it showed that this is very useful. We have here 2 systems, a slit container and a normal cylindrical container. Our entities are plastic pearls, which have a tip and a back, and these are different. The slit here is as wide as the pearl is thick. Randomly, from hand or by a machine, this was filled up. And then we count how many of the tips point upwards and how many point downwards. We don't account for the angular distribution because the sample is too small and it's too complicated, so we make a digital information. This is the table showing the result. We also did a one-dimensional study. 50% effective polarity by this formula we use also for the crystals, for the alignment, for the net alignment of dipoles. 11% for the two-dimensional growth and 5% for the volume. So, what is stochastic polarity formation? We have a feeding in one direction. We have asymmetrical objects, and they are randomly, Brownian motion then, approaching the surface, and they have a selectivity for their final attachment direction. Interesting, when we shake these containers, both here, we find that the polarity is completely disappearing. This is like nucleation. So this is really a gross phenomenon. We now go to thermal energy with an H, of course, and we discuss the water droplet. That seems to be trivial, but you will see it later, that the famous physicist was also coming back to this. The water droplet, I guess you agree all with me, has no net dipole moment as an object. There is no second harmonic generation, there's no pyroelectric effect. But these people here in nature have found that at the surface, the molecules on time average show a preferential orientation. This part where this orientation is active is about 0.3 nanometers thick. That means this system has a finite size. It encounters a border. At the border, roughly speaking, on time average, half of the interactions are active, the rest not. Inside, all interactions are active on time average. That can provide a selectivity. Therefore, such a system may split into a bipolar object having this kind of average polarity on that side and the other direction on this side, and inside nothing. We shall come back to this because this has a lot of analogy to a crystal seed we are looking at later. This here is a molecular dynamics simulation to demonstrate the same effect. We did not select water because of all the kind of difficulties handling interactions properly. It is CO simulation of about 100 to 200 molecules. We clearly see that on the surface there is a preferred sign of charge. So this system also orders in this way as the water droplet. We come now to theoretical models for the description of stochastic polarity formation. Let's go back to the pearls. We have a layer, we have an attachment probability, we fill the layer, we come to the next layer, and so on. A Markov chain is working like this. You have an initial state, you have a transition probability, you create the next state, and so on. This normally converges to a constant value. You can have a constant probability matrix or a variable one. This is perfectly working to explain the polarity formation by inclusion compounds, our first system where we learned a lot. The second method to do that, which gives similar results, of course, is the anisotropic 2D icing model, where we have a frozen layer as a substrate. We put another on top as a full layer, as an edge, as a kink, and we allow for thermalization. So, to speak, allow for configurational entropy. And then, by Monte Carlo simulations, we find also when this is growing layer by layer or edge by edge or kink by kink, this is achieving as well a constant polar order. I now review key results obtained for molecular crystals, for inorganic organic composite materials, and for natural tissues. First, state of a seed and growing crystals. This here is a key picture of the whole story. It's a model of a seed of 50 molecules long, 10 wide and 10 in the other direction. The molecules are such as iodo-nitrobiphenyl. They have an acceptor part and they have a donor part. They can interact AA, DD, AD, and laterally. These are the typical constants, feasible constants for the longitudinal interaction, and these are the transversal, the lateral interactions. They are set to negative, that when only energy is playing a role, this seed would be perfectly polar. But if we allow free energy and temperature, this is moving into this state. That means polarity is essentially found at the border, but antiparallel for the two ends. And in the middle, there is a tendency to reduce this strongly. This seed had only 1 degree of freedom to thermalize. That is the switch of the molecules within the chain. Here, only nearest neighbor interactions. So, this reminds us very effectively about the water droplet. Because this icing model could produce an artifact, we have used this here. This is a Monte Carlo simulation for a real molecule, no icing, nothing like this, where we have taken into account all the interactions, such as electrostatic, van der Waals, and all molecules are interacting with every other one. And we find exactly the same thing in 2D and also in 3D. So that gives us confidence that this icing model is able to, in principle, model this kind of a topic. The symbol now for this state, that seems to be the natural state of a seed when enough activation energy is provided that the system can thermalize this degree of freedom, is this bipolar notation that appeared for the first time in 1955 by Shubnikov in a nice book on textures. So we have either this state or this state. Now this brings us to the famous physicist I was addressing. Anderson was expressing his great astonishment he had as a student when Victor Weisskopf was telling him, look, and then he says, I was just told that nothing has a dipole moment. Anderson is expressing this in one of his last papers, which is very famous and is at the advent of mesoscopic physics. What does that mean in terms of statistical physics? We can say the thermal expectation value of a polar vector operator over space is 0 if we have no electrical external field. Now, our system has borders. So if we take an Ising Hamiltonian and take into account for series these borders, we can rewrite it into a term of bilinear and linear. And these linear terms have then the character of an electrical field. And they create this polarity close to the border. If you want to express with group theory, you can say the straight line where we have to use to project on and to define a polar property such as polarity has the symmetry infinity over m. And the field has infinity m. So if you act field on that, you get infinity. That means you get a polar domain. But going to a final size means that the crystal has to be bipolar because the plane is moving into the middle. Experimental means for the investigation of such kind of states. Scanning bioelectric microscopy is something, I will show you just an application. Phase-sensitive second harmonic generation, also I will show a picture, and piezo response force microscopy. We have developed the first two. The third one is appearing in literature and is extremely useful because it goes down to 50, 100 nanometer resolution, whereas these here more or less are limited to the micrometer range. This here is an old picture, but it serves as an explanation. It is the crystal 4-chloronitrostilben, where Hans-Beat Bürgi was working for several years, also with Venu sitting here in the audience. This is a crystal which topologically appears as it would be centrosymmetric, but it is not. It is, in a very simple description, P21. Now, this is cut, the crystal, to the plane where these two axes is present, and we see by the scanning bioelectric microscope that the crystal is bipolar. This is expressed by the two colors. Two crystals, same result. Then we go to this here. This is really a textbook picture. It was taken for an inclusion compound. If we make no phase, everything would be green. Now we make phase. That means we bring to interference a reference 2 omega with the 2 omega of this. If we do that, and the symmetry relation between these two domains, obviously, is an inversion or 180 degrees, whatever, then the phase shift is also 180 degrees, and we will get no signal here. When we turn then around the sample and the picture for your convenience, then the next domain will appear green. This is a very severe proof that this crystal developed into a bipolar state. We come now to this very strange thing of the reversal I was addressing at the beginning of the lecture, when I was addressing the point of the polar axis. This sketch here is telling you what we are going to look at in more details. We assume, maybe by kinetic control, to have a seat which is polar. We already noticed that this is not the natural statistical state. Then in one direction, we might find, in a simulation or in an experiment, that the crystal is growing in a normal way, admitting some defects. Nobody's perfect, that's not a problem. But on the other side, we noticed that there are many defects coming up. They are accumulating, and at the end of the day, the whole domain is flipped. That we call reversal transition. I will just show you a simulation where on the left side you see a picture of the uppermost layer, and one layer is moving towards you to tell you the last information of the uppermost layer. And on the right side you will see a side view developing then a cone which is expressing the reversal. Let's look at it. Clusters coming up, side view, cone is developing. You see? This is the way this system transforms into an opposite domain. This is not classical crystallographic twinning. There's no twin plane. There's nothing like that. This is stochastic twinning. We can make a cluster analysis by pencil, showing what the simulation is also telling us. Such kind as a confirmation. If we make this, we find that this side that shows in the simulation the transition needs about, at minimum, 4 molecules as a critical nucleus to develop the cone, and then it goes quasi irreversibly. The other side needs about 8 or more. So if you translate these 4 and 8 into probabilities, you will find that this is highly improbable and this is likely to happen. So, in principle, there is one transition, but it could well be for some energies, which we have to find in the energy space, that the crystal is sectioning in periodic domains, which finally, when we sum up, gives 0 total polarity. I have mentioned many theoretical aspects. Now let's go to a first confirmation of what I have said. This is again iodo-nitrobiphenyl, FDD2-MN2. This crystal was investigated many years before us by Gautam Desiraccio and by Sironi in Italy, and they all had big problems with the crystal. Why? Well, they had not at disposition these physical methods to see that this crystal is made of 2 domains. Now we have applied the pyroelectric scanning microscope, knowing the pyroelectric coefficient by another study, and we can say the molecules are oriented in this way, so the nitro group are on the surface. Then we have applied anomalous scattering for these domains, and we find flak parameter 1, 0, or 0, 1, how you take it. So this is a bipolar object. Question, how is this gap here looking? A bit for your relaxation, this Escherian type picture. We have, like Escher likes it, to demonstrate birds flowing both sides, but in the middle there is some kind of a metamorphose zone which convert them into the other direction. Now let's look closer to this transition zone. The first thing we notice is that this zone is very wide. It is about 150 microns. So this is not nanometer, this is macroscopic. And the normalized polarization is going from 1 to -1. Now to be sure that this is not something of just 2 overlapping domains of normal kind of twinning, we have made this frequency variation which accounts for the depth of penetration of our experiment, and that led us believe that is that what we think it is. That was the Escher. Now let's move on. When we have seen this, we were asking ourselves, what can we do to further improve the validity of what we are claiming? And for that, we have decided to look at solid solution. So we are making the system more complicated to create more phenomena and to see whether this is consistent with what we claim. For that, we have on the computer made a solid solution by these energies I have defined before, lateral, longitudinal, for an INB analog, where d iodo biphenyl was added. So a symmetrical molecule was added to this asymmetrical business. The intuitive answer is, what can that do? This is wrong. We see, without any of this symmetrical molecule, we have the normal transition, the reversal transition. Now, if we add about 10% in this smaller fraction into the computer, we see that in principle, this is a monodomain crystal, but the density of domains and also the size of clusters are different in these two domains. And if we move on in putting more, we get reversal, but inverted in the other direction. So this is a very strong proof of our mechanism. Let's look at the scheme here. This we had first, and then addition of DD-type molecule for a certain range of energy, I have to underline, gives this here. If in this case we would add AA, what would happen? The transition in the normal way, as it is here, would be enhanced. It would need less layers to be performed. If we change the energies, it could well be that addition of AA would make the inversion of the reversal. So, let's look for an experiment, whether this is true there as well. We have done this with iodo-nitrobiphenyl by adding iodo-iodo. It worked perfectly. But I would like to show you another system, which is 4-bromo-4-nitrobiphenyl. In case there is nothing added to a solution or to a gas, we have the normal reversal. But when adding now maybe 10%, 50%, something like this, we get the inverted color. That means we have inverted the reversal in the sense that now the bromo is at the surface and not anymore the nitro. When seeing this, dear colleagues, we were convinced that this is a real mechanism, not just a computer fake. I'm now coming to organic, inorganic, composite. It seems that these things have nothing in common, but we will see that they function along the same theory. These systems were extensively investigated by our colleague Rüdiger Kniep from the MPE Dresden. He investigated the growth of fluoroapatite in gelatin gels. Gelatin is hydrolyzed collagen. Now, what is found in the gel? At the very early moment of growth, we can isolate hexagonal crystals as normally apatite would appear. In the later stage of growth, we get something like an outgrowth, a bending, making this kind of double mushroom, or dumbbell as it is called, and the very end may end up with a closed sphere. So, how this comes about? Kniep and collaborators and others claim that the gel is somehow aligned by cations, which are Lewis centers, which can coordinate to this functional molecule. And then, when these are aligned somehow, nucleation starts on these threads. And these nanocrystals move together and form this kind of aggregates. We see them here in the nanometer range. Later, a mosaic crystal is composed of this form, where with some angle deviation, the z-axes are all aligned in one direction with some variation, and then more and more a spread to make the mushroom or the Blumenkohl. Okay, this is what we know about this system. Now, our question was, what is the polar alignment of these macromolecules in this composite? to our great surprise, these composites are also bipolar. Why we know the orientation of the molecule? Well, from the pyroelectric displacement current, this is one observable, and from a molecular dynamic simulation of a collagen model triple helix, showing us that the pyroelectric coefficient of such a thing is negative. By these two things, one calculation, one observable, we can derive that the orientation is like that. In such a case, we can never apply anomalous scattering. It's completely out of discussion. So we need something like that. Can we explain that? First, is this a unique phenomenon, or does this have some generality? For this, further going on than KNIP, we have investigated several biogenic minerals grown in the gel, such as calcium sulfate, oxalate, and a silicate. And all of them in the gel produced bipolar states. Then we were saying, let's select one mineral, and now let's vary the linear biopolymers, the linear ones. And we find that for gelatin, agar-agar, and coragenan, we have the same phenomenon. So this seems to be quite general. This is not something just valid for fluoroapatite. Now, come back to this. How can we explain that? Well, for this we have to investigate the seed. This seed is quite small and it's very difficult to find them in the gel, to align them, and finally to measure. But we succeeded. With second harmonic generation, we could demonstrate that this seed is polar in this direction. And in this direction, we don't get a signal. But the object is too small to make phase-sensitive second harmonic generation. So by this, we cannot demonstrate whether this is monopolar, monodomain, or bipolar. So we applied the scanning pyroelectric microscope. Here is one measurement, and here is one measurement. And we see we have done many seeds, as many as we could. They are all monopolar. So if there is one thing I cannot explain by today, it is how this gelatin molecule, these calcium ions, arrive to make this polar object. This is something out of our understanding at the moment. But this is not what we want to explain now. We want to explain why this object is bipolar. Well, if this is now growing, these collagen chains are interacting. They must be aligned because in the z-axis they are all directed. Biochemists have found out for natural collagen fibers that we have the following elongation reactions. We have peptide elongation and we have folds. A collagen fiber can have a fold and make a bipolar fiber. That you can find in literature with very nice pictures showing bipolar object by CC coupling. But the biochemists stress that there is no NN failure. That means, in terms of a Markov model, that we have the perfect condition of creating polarity because this here ensures polar continuation and this here ensures polarity formation, getting out of a random starting point of the Markov chain, because this PCC is significantly different from PNN. These are the error probabilities that makes the phenomenon, not the replication. Now, in our gel system, of course, we have not the assistance of the whole biochemistry making here true bonds. But in terms of Desirachou, we can say we have syntones here, and we have syntones here, and obviously no syntones there. So it could go like this. Well, we have now our seed, which is monopolar. This seed will grow in this direction below as well. Why I haven't shown it? Well, because it's not interesting. There is no NN failure, and therefore we will have just continuation. So the alignment of molecules in the down way is already fixed. But the alignment of molecules in the upper way bears the possibility that we have a CC error, and therefore the chain is inverted. And that explains why this object is bipolar. And it tells us that even this system shows a reversal transition. Clear that this works now by this scheme here. We come to natural tissues. Something that seems to be even more far away of our pearls at the beginning, the small molecules, the composites. When we go to study this, we see that in the cell we have a machinery which creates these collagen molecules. Then the cell is transporting them, modifying them, and finally by channels where extrusion takes place, they are aligned in this form. This is known for a long time. And then at the end, mineralization takes place, so to say that in between these organics, microcrystal, nanocrystals of inorganic materials come in. But we know, of course, from the crystallography of these materials that none of these minerals is polar. So the whole polar story has to take place here. How that could be? Well, if you take linear polar chiral objects and you just assemble them like cylindrical bars without taking care of up-down orientation, you will get infinity 2. This is chiral because you cannot escape chiral symmetry because the material is homochiral. So, such an object is just piezoelectric with transversal shear components, Dijk, but no diagonal elements. So we need a mechanism which allows to align these in the same direction. And of course, this goes back to this, now with the assistance, of course, of the whole biochemistry. Now we have real bonds, peptide bonds, and here a bond, but no bond here. So again, the Markov story comes to play because we have CCC different PNN. That allows us to compare now the phenomenon observed in vitro and in vivo. In vitro, we have assembly of these fibers plus the mineral from the front side, because this composite is growing from the front. In vitro, we have feeding from the back side, because the cell is extruding this ship from the dock. So they are fed from the back side. This means if the mechanism is the same, then consequently N is at the surface for the vitro and C is at the surface for the vivo. Because of the feeding, this is the only thing that changes. Now, is this true? Well, we have measured mouse bone with our pyroelectric microscope using our knowledge that most likely the pyroelectric coefficient of a collagen triple helix is negative, and then we get full agreement between the observation and the prediction. This means, dear colleagues, from the pearls to the single crystals of small molecules to the composite, to the biology, we have the same unified theory behind it. The next thing that remains, and I have addressed that in our review paper for this Congress, is the cellular polarity. Cellular polarity, as the biologists say, is essential for the function of a cell. If a cell loses its polar structure, it is subjected to make cancer, for instance. So, understanding the polar organization of a cell is something up and consequently in line of our analysis of polarity generation by stochastic methods. I'm coming to a summary. 0 versus 180 degrees disorder of building blocks combined with an unidirectional growth is the ground for stochastic polarity formation. Markov chain, as a simple explanation, can tell us what is the polar order and what is at the growth front. This can also be done by this 2D anisotropic Ising model. Now comes the essential point for the polar crystals that are nucleating into a polar seed. Polar packing of dipolar molecules shows a non-zero probability to undergo a reversal transition into a bipolar state. I think this is completely new for crystallography. Final claim. Consequently, a monodomain polar state of a molar crystal is not the true statistical state. Now I come to a proposition, because we have not yet done that. I would like to come back to this extreme gross anisotropy of crystals observed. What could we do to understand this probably? We should measure the anomalous scattering of several of these materials. We should measure the gross anisotropy, so to know which phase is not growing. Then we should take the best force field method to elaborate at which site defects are more probable. And then if we find that the phase that is not growing is that where also the probability for the reversal is highest, we can say that we have kinetic hindrance, sometimes in literature called self-poisoning, which hinders the growth in some systems. In other systems, like iodophore-nitrobiphenyl and others, the transition is going on. But this transition must not always go on. I come to the acknowledgement. I would like to acknowledge all my older collaborators, some of them now professors. I would like to acknowledge many colleagues with whom I had very good collaborations over the year, such as with Michael Wübenhorst. Together we developed the scanning bioelectric microscope. With Piero Macchi, with whom we actually do these field calculations. Professor Bürgi from Bern, who helped us at the beginning with the understanding of the Markov model, and so on. Dear colleagues in France, this is more or less my goodbye lecture, because I'm going to retirement at the end of 2018, and then my laboratory will be closed because we have decided to move to energy research because of Fukushima. Okay, at that point, I have nothing left than to express my deep thanks to all the colleagues in France who have so nicely received me over these many years, given me chance to organize microsymposia, lectures. Even I'm not a crystallographer. I've never saw the structure myself. So thank you very much.
Okay, so thank you for that very, very insightful presentation. So we have time for questions. Over here.
Thank you. Very interesting. Very simple question. Are the systems also ferroelectric?
Okay. Ferroelectricity, of course, is something different. This is something very much related to a lattice, to lattice properties. These systems are absolutely not ferroelectric. But ferroelectrics, they by entropy also have a tendency to go into a state of zero total polarity. The monodomain state is not the F state. There is a similarity, but these are never ferroelectric. You cannot switch them by an electrical field.
In one slide you showed the nucleation mechanism. So first question is it homogeneous nucleation or heterogeneous nucleation?
Okay, I'm not so much talking about nucleation. I was just addressing the state of a seed. Nucleation is a highly cooperative mechanism, which would need an extra analysis. This is out of our consideration. We start from a seed that is already there, and then we look at the statistical state of that seed, but we don't give a mechanism how these seeds comes about. We are one step later.
Then second one is that nucleation mechanism or the growth study?
Okay. First, we always have nucleation, and then comes growth. And when growth starts to play, this orientational disorder comes in and may give rise to a development of a property towards purpose. You see? That's the way we look at it. Investigation of nucleation in this respect is very, very difficult. You would need a high vacuum system and maybe a scanning piezo response microscope to look at nanometer-sized object. This is feasible, but nobody so far has done that. It is extremely difficult and delicate. Okay?
Thank you.
So you have observed the transformation from a monopolar phase to a bipolar phase. Is it permanent?
Okay. Once this transition has taken place and the crystal has reached a certain size, that never changes. But, of course, this is somehow a kinetic stabilization. If we would go back to thermalization of the whole system, it would behave differently. Now, if we go back to our seed that was showing this bipolarity, 50 molecules long, if you make this longer and longer and longer, and you allow this full thermalization inside you have zero polarity, and at the border you have a nanometer thick layer, which is polar. So this is switching very much to the surface, like in the water droplet. We come always back to this water droplet, okay? Yeah, there's someone behind.
Behind.
The transition probability, or the kinetics associated with the reversal is so large, and you have transition probabilities that are effectively dependent on the initial orientation of the seed. Does the seed really create a deterministic or near deterministic development of the orientation of these bipolar phases?
Okay, if we have a seed and a certain set of energies out of the space of interaction energies, then the thing is given and deterministic. It will go to this side or to this side for reversal.
Mm-hmm. Okay.
It is determined. It depends on the interaction energies. This today we can elaborate by force field calculations. We have done that. Some part is appearing in the paper which is attached to this conference. You find something therein.
Okay, so is a lot of this stochastic approach
well,
allowing the reversal more of a thought experiment on exploring these types of energy spaces?
Yes, the reversal is due to a stochastic that is a conditioned probability to occur. This is the essential point. You need this 1 degree of freedom of the molecules. Mm-hmm. Then this can happen. Okay? Of course, in a finished crystal with large molecules, you will never see this kind of a flip. But there are molecules such as CO or something like that, or iodo, 4-iodo-toluene. There it's very likely you have this, okay? So it depends very much of the system. But I'm talking in principle. And then we look for particular cases. Some kind we have it, sometimes we don't have. And we have reasons why we haven't not seen it. Okay?
Yeah, very interesting. Thank you.
So I have a question over here. My question.
Okay.
So I think it's, we're all very fascinated by the seed situation. And I'm not sure how to ask this question, but is it necessary, is it true that we know the true composition of the seed itself?
I didn't understand.
Do we know the composition of the seed?
The composition of the seed. Okay, if we have only one molecule, the composition is clear. Mm-hmm. If we have a solid solution, of course, then in the seed we might have a certain amount of the second component. But this is already not necessary to explain what I wanted to say, because the seed may be polar, and then this solid solution story starts to become effective. Of course, it could already be in the seed, but that will not change the situation.
But I'm also wondering, could you have a, so the conditions to grow the crystals, what are they exactly?
Okay. Best we grow the crystal under conditions where the supersaturation is lowest. For the theory, we have a limit that the supersaturation is 0. It will take another 10 years to make a theory now of the kinetics of the whole story. So I'm discussing all in a limit of very slow kinetics. So the whole thing is not a kinetic effect. And not having done the work, we can say that the kinetics probably will modify a bit the result, but it will not turn it over. That we can say.
But is it also possible that the seed could be a solvate, for example, that transforms into...
Yeah, the seed can do whatever. I was not addressing the particular nature of the seed. Mm-hmm. I was talking of a monocompound. But of course, in the inclusion case, we have two components. We have the channel maker and the filling of the channel. Now, for the inclusion, we assume that nucleation most likely is creating a centrosymmetric seed. And then the Markov process starts to become effective when channels and inclusion simultaneously build up the growth.
Okay. Thank you.
Thank you very much also.
Okay, so any further questions? I think we're at that time. So as Jurg mentioned, this is at least for this situation, somewhat of a farewell lecture. So we've appreciated your contributions.
Thank you.
Greatly. So let's thank again for a great talk. And then I must call up Kumar Barada, who's going to close the session.
So this is on behalf of LOC.
Thank you very much. Very kind.
Thank you. Thank you all.
Okay.
Thank you.